Right, now we want to talk about the types of solids that we can have. And so there are four primary types of solids we're going to talk about: metals, ions, covalent network, and molecular solids. And these four solids are characterized based on how the particles are held together. Amorphous and crystalline would describe a particular version of one of these solids. So if you had a molecular solid, it could be crystalline or amorphous. You can have a metallic solid that's crystalline or amorphous. And so when we're looking at this, this is going to be looking at kind of what holds those atoms together. Amorphous crystalline is going to be looking at what what is the pattern of those atoms or molecules in that solid. First type of solid we want to talk about are ionic solids. And this is something we're familiar with from previously discussing in types of compounds, because all ionic compounds exist as solids. So ionic solids are just the ionic compounds. And in an ionic solid, you have a repeating structure of ions. That's your crystal lattice, right? You have these ions that form via the transfer of electrons from anion to cation. Or cation to anion, sorry. And then you have these opposite charges that are attracting each other that hold these ions together in this crystal. So ionic bonds, a chemical bond, is what holds these atoms together in this solid. And so this chemical or this crystal lattice of repeating kind of ions taking on this structure is based around basically maximizing the attraction or the kind of exposure of positive and negative cations in some sort of arrangement. And so in table salt, you do have this cubic arrangement or cubic pattern that shows up of basically sodium and chloride ions. And so they're kind of going back and forth. And then eventually you can make salt crystals. These are very, very zoomed in with a microscope salt crystals that are little cubes that are reflecting the cubic nature of these atoms that are arranged in that pattern. And so when you're looking at forming these, whatever the type of ionic compound is with whatever its chemical formula and all that, the crystal structure that forms maximizes the contact between oppositely charged ions, because the positive and the negative is what actually, that attraction is what holds the molecule or the solid together. This is a negative chloride and this is a negative chloride. Those are not attracted to each other. So it's just the positive negative and the positive negative. There's a lot of ions jammed in there together though. So there's one particular arrangement that holds it. And that's why ionic compounds are always going to be crystalline, because amorphous doesn't really work. There is only one way that these things are going to be able to stick together. That's really, that fact that you have these really strong ionic attractions that are really kind of set at one region really affects the properties of ionic compounds. So the first one is that they have very high melting points. It is extremely difficult to melt ionic compounds. So like table salt, you've never seen liquid. I hope you've never seen liquid salt. It requires extremely high temperatures to melt ionic compounds. It is possible, but very, very high temperatures to melt it. Because they have that chemical bond holding them together. It's really strong attractions between everything. But they don't have high hardness. If we think about hardness, it's about scratching, it's about breaking. When you take an ionic compound or an ionic solid, and if you perturb it a little bit, so you're taking a hammer and whacking it onto the piece of salt here, you shift the atoms a little bit, and now you can see, instead of it being this positive negative contact here, positive negative contact, it becomes negative negative, negative negative. That becomes the type of contact, and that is repulsive, right? All of a sudden, the solid, instead of being held together, is being pushed apart. And so ionic compounds have low hardness, so it's relatively easy to break a piece of salt. It's hard to melt it, but you can break it up into little bits. It's very crumbly. It's very easy to break it with your hands if you have a piece of salt. Ions are charged, so you might think that they would be conductive. We're used to salts being conductive when we dissolve them in water, but ionic compounds themselves are not conductive at all. Liquid salts, if you melt them at these very high temperatures, are conductive. That kind of, you're kind of flowing electrons. So generally, you do need to have a liquid ionic compound or dissolve the ionic compound in, say, water, and you will get a conducting solution. But solid ionic compounds do not conduct. The next kind of solid is going to be molecular solids. So we saw ionic compounds. We're used to talking about covalent molecules. So any molecule you've ever drawn a Lewis structure for, or seen a Lewis structure for, when that compound forms a solid, if you freeze that compound, it will form a molecular solid. And the reason why it's called a molecular solid is that it's a bunch of molecules held together by intermolecular forces. There are no chemical bonds holding together the molecules in a molecular solid. It is only intermolecular forces. So dispersion, dipole-dipole, and hydrogen bonds are what are holding everything together. Because you can kind of imagine, in the case of ionic compounds, it was strong ionic bonds, high melting point, because we have only intermolecular forces, which are relatively weak. Molecular solids have low melting points and low hardness. Right? There's not really much holding molecules together. It's just an intermolecular force. There's also no conductivity. The molecules aren't touching each other. It'd be hard to flow anything through it. So molecular solids are generally not that good at solids. Most of the chemicals that you interact with that you think of as molecules, that function as molecules, for example, drugs, like this is the solid of ibuprofen, are molecular solids. And so it's just this is an ibuprofen. These are each, I have 1, 2, 3, 4 ibuprofen molecules, and they are arranged in this sort of crystalline structure. It's still a crystal, that there are repeating patterns of molecules, that they're arranged to basically have their intermolecular forces, in this case, hydrogen bonds, where the molecules are going to line up so that you can have hydrogen bonds between these particular atoms. And so they arrange like this. Most drugs, most foods, most things you interact with that are not ionic are molecular solids. Most solids they interact with, not things. And you know, the relative orientation of molecules in a molecular solid is going to kind of be locked in place to maximize the intermolecular action. So we know water molecules can form hydrogen bonds. And so in the liquid, they just kind of bounce around and relatively arrange themselves such that they can form hydrogen bonds to some extent. But in ice, the molecules are going to be arranged perfectly, such that there's a maximum number of hydrogen bonds between each kind of neighboring water molecule. So they're arranged in a pattern such that it's like each water molecule is forming 2 hydrogen, like donating its hydrogens into 2 other molecules, interacting with 2 others in a different way. So it's just this huge network with all of these molecules interacting with each other to form as many hydrogen bonds as possible, all maximized, all lined up perfectly. And that's always going to be the case in a molecular solid. So in something like a dispersion-based thing, it's going to be a little less kind of ideal, but hydrogen-bonded molecules especially have a very rigid structure, very particular, not rigid, but particular structure that they do take. So you can form solids that are bound together by covalent bonds, and we call those network solids. You'll also see them called covalent network solids to really drive home the point that it's covalent bonds holding it together. So just like in an ionic compound where it was chemical bonds but ionic bonds holding it together, in this case, because it's covalent bonds holding the solids together, they have very high melting points. If we think about, melting, you're going from the solid into a liquid. You're breaking that contact, right, to move the atoms around or the molecules around. In this case, you'd have to be breaking a covalent bond, right? So that's 10 to 100 times stronger than intermolecular forces. So, molecular solids, very easy to melt. A lot of times you'll hear the idea like, quote, covalent compounds are easy to melt. That's only molecular solids. Covalent network solids have some of the highest melting points. So diamond is a common example. Diamond, if you remember, was our kind of star hardness. That's because it's really hard, because in order to move the atoms around in a piece of diamond, you have to break a bunch of covalent bonds, right? If you're going to break a piece of a solid, you have to break all those bonds. That's a lot of covalent bonds to break, and that's really hard to do. Graphite is another covalent network solid where the atoms are all bonded together by covalent bonds. Very held together very strongly. There's kind of a layered structure of graphite. The layers can move over each other, but within each layer, very strong bonds. Covalent network solids also not conductive. They don't really want to change much. They don't want to flow much. It's just kind of locked into place, very rigid, very high melting points, very strong, not changing much at all. The final solids are metals. This is a very common metal that type of solid that we interact with every day. And so metals are known for being highly conductive. Their hardness is really variable because that's about scratching. Some metals are very hard, some are not. There's a lot of metals, but they're always workable. And we'll talk about what that means. That's a really important property. And atoms in a metal, they're not held together by ionic or covalent bonds. There's no ionic bonds, there's no covalent bonds in a metal. There is, unsurprisingly, called metallic bonding. And so in a solid metal, so this is a solid metal where there's a bunch of metal atoms lined up together, or all backed up together. Valence electrons are not really bound to particular atoms. You know, in ions, we know electrons are transferred, and then they're between, you know, they're on the cation and anion, they have their kind of own atoms. And in the case of covalent bonds, atoms are shared between particular atoms, right? These atoms have formed a bond. Metals are a bit more loose, a bit more just kind of flowing around. A lot of times you'll hear it called a sea of electrons. Now you have all of these metal atoms, and then there's just kind of these halos in this image of these electrons. They're just kind of moving around. Now this is a pretty complicated quantum mechanical thing that's going on with the electrons. We don't need to worry too much about it, but we do just need to know that we call it a sea of electrons and that they're kind of free. And it's important, the fact that these electrons are not specifically associated with particular atoms or pairs of atoms, like in the other types of bonding, is what allows for conductivity. You know, the flow of electricity is really the flow of electrons. And so in order to have a conductive material, electrons need to be able to move. And it basically works, in this case, you can kind of have this hopping, you know, an electron comes into here, the electron that was there is kind of moving along here, and they can kind of flow down the path one to the other. And so that's how you can flow, and it only is possible with this sort of sea of electrons or metallic bonding. And so there's no directional bonding, right? The electrons are just kind of freely moving around, holding everything together. And that makes a very important property in metals, that metals are workable. So you see this machine, the piece of metal is being bent into a different shape. You can work the metal, you can put in energy to change the shape of the piece of metal. That's a property unique to metals. All the other things that we've talked about, molecular solids, ionic, and network, just would shatter. They would just break if you tried to do this. Only metals can do this. And this comes from the atomic level that accommodates this, right? When you stress something, when you try to break a material or move it, you're going to have to move atoms around. And it's important that in metals, you don't have, electrons aren't associated with particular atoms. You don't have particular bonds between particular atoms. So as the material starts to move and deform, atoms can kind of shift around, right? Like, oh, they've kind of moved, some connections between atoms or some atoms touching each other kind of fell apart. So they can kind of slide around and move to accommodate the stress, accommodate the deformation. So that's really important in metals, and it allows for this workability. That is a unique property of metals that's really, really powerful. And so we have these four types of solids: metallic, ionic, covalent network, and molecular, and they're really all defined by what holds them together, right? Is it metallic bonding? That is the only thing that will give you conductivity. Is it ionic bonding, giving you really high melting points without high hardness? Is it covalent bonds, which high hardness, high melting point, high rigidity? Or is it molecular solids, which are held together by intermolecular forces, which are the weakest of the bunch, which isn't necessarily a problem. That just informs their properties. Sometimes it's good to have materials that are a little more kind of breakable, right? That you can work with, that you can break apart, that you can melt easily. That'd be a good thing for like foods that we eat. You know, it's helpful. It's an important property of butter that you can melt it at a low temperature. It's a molecular solid, but that's okay. Just don't want to make your house out of butter. All right. More solids to go. We're getting there though. Participation 120 is what we're looking for questions on. Just a couple more videos in this set. See you in the next one.